Hi, welcome back everybody. I am going to talk a little bit more about some EPR calculations performed in ORCA. So in the last video I had described some of the EPR characteristics of this molecule that was the product of a nucleophilic attack between an N-heterocyclic olefin and a cyclic alkyl aminocarbene. So this is one of the spin density plots obtained from calculations with ORCA, and the compound basically it has this structure for R that when oxidized one time it gave a radical, and after that it produced other diamagnetic products through H abstraction from the solvent or different side reactions. These compounds are quite reactive and quite unstable towards oxygen. So we had chemically oxidized the previous molecule and obtained this radical and obtained this nice EPR signal. There were three molecules with different substituents, and only one of them gave a stable EPR signal. We could simulate this quite well considering 3 nitrogens with these hyperfine splittings and 2 hydrogens. And we calculated the spin density, and basically the spin density shows reasonable values for 2 nitrogens, another nitrogen here, and a couple of hydrogens, one bound to this carbon radical, which would be the main radical, and this other hydrogen in red is not well seen in this perspective, but it's on the vicinal carbon. So everything was fine. We submitted the paper, and then one of the reviewers said that basically the hyperfine splitting seemed to be too low, and that if we could actually calculate the hyperfine splittings with ORCA to compare with the experiment. At the time I thought that was slightly annoying because the spin density seemed to clearly show 3 nitrogens and 2 hydrogens. The fitting of the EPR spectrum was perfect, so what's the necessity of calculating hyperfine splittings? But then we started doing some of these calculations, and actually, so here in the first line is the experiment. So all the values are around 6 megahertz. But originally for this radical, it was calculated that all the hyperfine splittings were considerably larger. Values are around 13 to 14 megahertz for the nitrogens, and even minus 58 megahertz for the hydrogen. The sign is relevant for the calculation, but in the simulation you take absolute values. So basically this could not be. I did not do this particular calculation. It was done by other authors in the paper, but then I started calculating for the same molecule with different options. So this is TP-SSH, which is a function which I really like and usually get nice results for EPR related properties, spin densities and other characteristics, and using a SORA def2 TZBP. SORA is the relativistic approximation for dealing with relativistic effects, which it's not really necessary in this system, but well, I'll discuss why I use it. So basically this was the structure that had been optimized at another level of theory. Then I did all these calculations and always got a much larger value of the hyperfine splitting, particularly in this hydrogen, and all the other values were quite large. I tried different options, SORA def2 QZVPP, which is a very expensive basis set. Then I re-optimized the structure at the TP-SSH def2 TZBP level and obtained slightly better values, but still they were far off. And I tried many different options. I even tried omega B97XV, which is considered in the Grimme paper about the density functional theory SU, is one of the best functionals that reproduces energetics overall for many systems. I had tried before originally these calculations with different pseudo-solvents. They don't make much difference. So basically what I'm saying is that I was obtaining values which were far from experiment with many different options. And I illustrate here so that you can see how much of a difference you can get in values by changing functionals, changing basis sets, changing pseudo-solvent. So it's not a really large difference. So then I said, okay, now I don't really believe that I am having the correct structure, so I started trying different things. This is the original radical with the spin density, but I also calculated the decationic radical equivalent. I also calculated a neutral radical if it had somehow deprotonated. And finally, I calculated a variant of this molecule with a OH instead of an H in the carbon radical. And I calculated several other variants. So here are again the experiments. For example, using a counter ion triflate did not really change the results from before. Calculating the deprotonated neutral radical gave even worse values, 30, 20, 25, 29 megahertz. Protonating the radical gave even worse values for one of the hydrogens. And finally, calculating the OH variant gave results which were much more in accordance with the experiment. They were still a little bit off, a little bit high in the nitrogens, but the hydrogens finally gave values which were much more similar to experiment. So this is basically to show that in some cases you have to calculate things carefully and not trust just an intuition or a simple superficial analysis of the spin density, and that in some cases you can use a calculation to really see that something in the experiment doesn't match, and you can actually propose another molecule or another variation. So I'm not saying that this is exactly the radical that we observed, but definitely whatever radical we observed had to have one extra, at least, atom near the radical region, because the spin density was overall too high in all atoms, and all hyperfine splittings were considerably higher than experiments. So basically, more atoms were needed to delocalize that spin density and reduce the hyperfine values. And also, in this table, I think that you can use it to have an idea, at least for a relatively simple organic radical, how much of a difference you can expect by changing different parameters. And my conclusion would be that if your theory level is good enough for organic radicals, you would not expect a really big difference. Notice that the values really change when I re-optimize the structure at a different theory level. So that's one thing to consider, that the structure should be as realistic as possible. So this is all for this video. I want to thank people who have subscribed. Now last week I passed 100 subscribers. It's a little milestone. So please, if you have any comments or any requests for future videos, let me know. And if you like this video, please subscribe and share. Thank you very much.